Today, I'm presenting VeriSMo, a formally verified Rust-based security module for AMD confidential VMs. To protect sensitive data inside a VM and remove the trust from hypervisor, hardware vendors have introduced new hardware features like AMD SEV-SNP, Intel TDX, ARM CCA to protect VM security and prevent hypervisor attacks. And in our work, we utilize the AMD SEV-SNP to build the confidential VMs. However, since hypervisor is no longer trusted, the security feature that was provided by the hypervisor should be moved into the VM. For example, hypervisor-based code integrity and hypervisor-based virtual TPM that was used to provide runtime attestation report for the OS workloads. And all of those features should be moved into a security module inside a VM. So what does the security module do in practice? The security module is a VM firmware that runs at the highest privilege level and provides APIs for the guest OS to send a request. And we can replace the hypervisor-based security features, including code integrity and virtual TPM. And also, the security modules will help the guest OS to manage the sensitive security changes to the VM, including the CPU context and the SMP memory states. And for example, you can change the memory states, permission access permission, and change the page to a private or shared. Since the security feature is very critical, it's not reasonable to run the guest OS and security module in the same security domain. And to isolate them, we utilize the VM privilege level provided by AMD to run the guest OS and security module in isolated environment, so that they will have isolated memory and CPU states, while only sharing the VM memory encryption keys to defend against hypervisor-based attacks. Similar to any sensitive software, the security module needs to maintain some security properties, including confidentiality and integrity. And we can leverage the AMD provided hardware features for memory encryption, and we can leverage the VM privilege levels based memory isolations to keep the confidentiality to defend against hypervisor and malicious guest. To protect the integrity, AMD also provides us a reverse map table to help us to prevent hypervisor from mapping your virtual address to different physical address. And in this way, we can guarantee the memory integrity. However, those hardware features are still controlled by the software. And the use of the hardware features from AMD SNP is very complicated. Specifically, when we run security modules, the security module can validate or invalidate page mapping in the reverse map table, and it controls memory encryption in the page table, and can change the virtual CPU context for the guest OS by modifying the VM safe error page. And improper implementation of those changes will be super critical for the security of this security module. And to be worse, the security module also have very complicated concurrency issues. First, VeriSMo, the security module can run at multiple CPUs. That means we have to guarantee the memory safety under concurrency. And second, we also have multiple entities that can have concurrent access to your shared hardware resource. And the concurrent access from the malicious guest OS and hypervisor is not verified and runs in different security domain. So when we are considering about memory safety, we have to consider our potential combination of the operations from the guest OS and hypervisor. And since the security for security module is so critical, existing open source security modules choose to implement their code in Rust. However, implementing in Rust does not fully guarantee the security. Specifically, for those open source SVSM modules, they were written in Rust, but with a lot of unsafe Rust, because they have touched the raw memory and used the registers. And also, they are never formally verified to be cracked to use the hardware access to change memory states and change CPU states. To guarantee the correctness of the security module, we implement the VeriSMo and use formal verification to check the security property holds under the trusted hardware and untrusted software combination. And specifically, we use a Rust-based formal verification tool, VeriSMo, to formally verify our code and make the Rust even more safe when it privates the low-level codes and which controls the memory and CPU registers. And thanks to this state-of-the-art verification tool, VeriSMo, we can implement our VeriSMo code, including executable code, specification code, and proof code, or in the Rust language supported by VeriSMo. VeriSMo is built above the Rust ownership, borrow, and type tracker that provides us an ownership-based tracked permission that allow us to reasoning the memory safety similar to the separation logic. And also, VeriSMo provides optimized performance so that we can efficiently verify our code base in a very efficient way. So to make our verification to be aware of the attack model we described earlier, we first model the machine states with multiple basic operations related to memory and CPU registers. And those operations could be done by different entities, including VeriSMo, the guest OS, and hypervisor. And to prove the confidentiality and integrity for VeriSMo has to use the VeriSMo basic operation in a correct way. And to encode whether or not VeriSMo can use in correct way, we define the precondition to restrict the use of those basic operations for VeriSMo's basic operation. And once VeriSMo following the precondition to use these basic operations, we can formally prove that the VeriSMo will achieve confidentiality and integrity no matter how guest and hypervisor use their basic operations in any order or sequence. And then the question is how we could track these machine states. And at implementation level, we utilize the VeriSMo provided tracked permission technique to track the resource permissions to protect the access to those raw resources, including the raw memory, page table, RMP table, lock, and control registers for CPU. Specifically, if we want to track memory states, we could define a track permission and which is indexed by the guest virtual address. And the memory permission will carry the memory contents representing the data and the security labels to see whether the data is a secret or public. The tracked memory permission also describes the memory attributes to describe the access permissions that are reflected by your RMP entry and the page table entry. For example, we will carry whether or not this RMP mapping is validated and whether or not you have set encryption bit in the guest page table. So with the tracked states, we only need to ensure that we have a correct transition of the memory states, and also we use the memory states in a correct way. Here, I will give you an example how we safely access the raw memory. Initially, we will have memory states from initial states. It's invalidated and it's not encrypted, and its content is unknown. And we can call a make private function to transition the memory to a private states, which is has a validated mapping and has encryption bit in the page table set. And then we can write secret to this private page, since it's private to the VeriSMo and not accessible by hypervisor or guest OS. And then we can use a safe borrow to borrow a reference of the contents. However, later on, VeriSMo might need to communicate with external world. Then we need to use make shared function to transition the memory states to a shared states, indicating that we will make the encryption bit to 0 in the page table and invalidate RMP entry. And under these states, it's not safe to borrow a reference of the content because the content could be modified by malicious hypervisor or guest OS. And also, it's not safe to write a secret into this memory because this is shared memory and will link to malicious attackers. And to use this content in the shared memory, what we need to do is to copy the contents to another private memory. And then we can use the copied private memory to do the computation over this shared content. And to give you an idea how we could use virus to convert the unsafe memory access to the safe and formally verified functions, let's look at these dummy examples here. So here is a function that we want to borrow immutable reference using an integer represented address. And in the standard Rust, there's no way you can convert this function to be a safe function. And utilizing the tracked memory permission, we can pass a tracked permission reference to this function. And this tracked permission we use here is an unforgeable object without any runtime overhead and will be erased at a compilation time after verification. And we can define the precondition to check whether the code has the correct ownership for this memory block and whether this memory is in the correct state that you can safe borrow the reference. And then with the similar technique, we can convert all our security module code to use the virus protected and formally verified basic operations. And finally, we'll need to a fully proved security module. And in VeriSMo's implementation, we only have very small amount of those basic operations that are dominantly trusted, just like hardware, which they are just a wrapper of some hardware access code and also a wrapper for a formally verified crypto library, HACL. And based on these basic operations, we implemented our security module code, and to formally verify it, we also have around 2 times of spec and proof code, where the majority of them are for the model proving. And for this machine model proving, it could be reused if you are implementing in different ways with the same security model. And finally, we formally verified 4,000 lines of executable Rust code in 3 minutes in the multi-thread mode using virus. And we noticed that when we implement this VeriSMo using tracked permission, it incurs nearly 0 performance overhead. And that means this is a very efficient way we can use formal verification to implement a security module. And in our verification, we also noticed a very tricky bug during our evaluation section. And here, this is a very simplified version of the function that contains the bug. It's a function to help the guest OS to make a memory page from shared to private. And intuitively, if you read this code, you'll figure out there is a check to check whether the page belongs to a guest OS and whether it is shared. And only when it belongs to a guest and it was shared, our code will validate the page and then assign the page to the guest. It seems that this page should never carry the security module secret because this page is used by guest OS and it's shared. Unfortunately, this is not true. Could you think about why this code is not secure? That's a very interesting bug. And even you cannot think about why it's not secure, don't worry, you are not alone because this is exactly the original thoughts from the open source SVSM developers. And they only fixed the bug after we report this security issues with them around 1 year ago. And specifically, at a very high level, the bug happens because the hypervisor can change the memory mapping to a secret physical page before you run the validation instruction. And then, since the security model is unaware of this change, if it assigns the page to the guest OS, then the guest OS will be able to access the VeriSMo secret. And this is unexpected. And if we run our verification tool, and it will show that the verification fails because the memory is not guaranteed to carry the public contents when we run the ARM adjust to assign the page to a guest OS. So to fix the bug, it's very easy. You just need to sanitize the content between the validation and the permission adjustment operation. And after adding the sanitization, our verification succeeds, demonstrating that this code uses memory and in a safe way. To conclude, VeriSMo is a fully verified Rust-based security module for confidential VM that is not only cryptographically attested by hardware, but also formally verified. We can effectively verify over 8,000 of executable code using the tracked permission technique, which demonstrates the power of the formal verification. And also, we can utilize the formal verification to detect a very deep bug that can be very easy to be missed by code review. And our performance is very outstanding, and you can refer more in our paper to understanding how we evaluate it and how we compare with unverified code. And our code is also available online. Thank you, and I'm happy to take questions.